In the previous sessions, we have discussed about the Joule-Thomson effect and have defined an important parameter known as the Joule-Thomson coefficient for a gaseous system. And as per our derivation, the Joule-Thomson coefficient mu is given by dou T with respect to dou P at constant enthalpy. We have further shown that mu can be expressed as 1 by Cp times T into dou V by dou T at constant pressure minus V, which was further simplified by introducing the volume expansivity beta of the gas as V by Cp into beta T minus 1. So these are the different ways in which we have expressed the Joule-Thomson coefficient for a gas. And we have seen that the relevance of this quantity is that it's a measure of the change in temperature of a gas with pressure during a constant enthalpy process. Means whether or not the gas will be undergoing a cooling effect can be determined from the value of the mu for that particular gas. So in short, I can say if the mu of a gas, the Joule-Thomson or Joule-Kelvin coefficient of a gas is less than 0, if we find mu less than 0, then we can say that the gas will be cooling down. The gas will be heating up, or we can say the temperature of the gas will be getting increased. Now, if mu is equal to 0, for any gaseous specimen, then we'll see that T will not change. So T will remain a constant. There is no change in the temperature. And the third case is that if mu is greater than 0, means the value of mu is positive, you can just check in what all cases it will happen. Then we'll see that the temperature of the gas will get reduced during a throttling process. Means the third case corresponds to cooling. So depending on the value of the Joule-Thomson coefficient, the gas sample may undergo heating effect, cooling effect, or it can remain a constant temperature. Right? So in order to verify this one, you can check. You can see that mu is given by equation number 1, either this quantity or it will be determined by this quantity. Since Cp and V both are positive, the sign of mu will depend upon the quantities in the square bracket. So you can also express these things in terms of the quantities in the bracket. So by comparing these quantities with the counterpart in the bracket, you can just say whether it will be undergoing cooling effect or heating effect. And that is what we have done in the later part of the previous videos. Now in this module we will discuss, or in this video we will discuss the Joule-Thomson coefficient for an ideal gas or a perfect gas. An ideal gas is otherwise known by the term perfect gas. We mean the same, perfect gas. So to do that, let's all this information or the behavior of any gaseous system is contained in its equation of state. So we'll begin with the equation of state for an ideal gas, and let's consider for simplicity 1 mole of an ideal gas. So for 1 mole of an ideal gas, what's the equation of state? PV is equal to RT. PV equal to nRT becomes PV equal to RT. So let me say this is my one of these. Okay, so since I have already named the other equations, so 1, let me call this is 2, right? PV equal to RT. Now I'm going to use this equation for mu. Okay, so this particular equation I'm going to use. So let me find out what is dou V by dou T at P. So therefore I can differentiate with respect to T, keeping P as a constant. So what will be the thing? So P is a constant, so P into dou V by dou T. So it's understood that I am keeping P as a constant, so let me put it P. So what will be on the other side? So it will be simply equal to, just a minute, okay. So it will be simply equal to R, right? So that is equal to R. Therefore if I multiply this quantity, right? Okay, therefore I can take this one is equal to other way, dou V by dou T, because I'm interested in that quantity. We separate out, at P will be equal to simply R by P, right? Or simply if I multiply throughout with T, therefore T times dou V by dou T at constant pressure. You know the motivation, because I'm going to use this particular equation, okay, for mu. That's my purpose. So what will be that equal to? That will be simply equal to, I have to multiply with the T on the other side, so RT by P. And from equation number 2, what will be RT by P for an ideal gas? So it is nothing but equal to V, which is equal to V, right? So RT by P, RT is equal to PV or PV, P and P getting answer, whatever it is. Okay, so this quantity will be equal to V. So that is equation number 3. That gives you some insight. Okay, so let me use equation number 3 in equation number 1 directly, right? In the first equation of equation number 1. So what will be that? So 3 in 1 will give mu is equal to, right, directly 1 by Cp into, what is that, right, 1 by Cp into the first term we have proved that is V, and so V minus V it becomes, and that's equal to 0. Yeah, and that is a very notable result for us. And what we have proved is that for an ideal gas system or for a perfect gas, the Joule-Thomson coefficient mu is equal to 0. What does it mean? It means that mu equal to 0, we have discussed the second case. Whenever mu equal to 0 for a particular system, it means that the throttling process will not change the temperature of that system. So if mu equal to 0, the throttling process, or better known as the porous plug experiment or Joule-Thomson experiment, will not produce any change in the temperature. There will be neither a heating nor a cooling. Or we can say that the ideal gas does not show Joule-Thomson effect. That is, no Joule-Thomson effect. That's a very, very important result for an ideal gas, because mu has been obtained as 0. There is neither a cooling nor heating, right? So hope you remember in our introductory session on Joule-Thomson effect, I had mentioned about this point. Since ideal gases do not show Joule-Thomson effect, means no cooling or no heating, we can use the Joule-Thomson experiment to distinguish between an ideal gas and a real gas, or the nature of the gas, nature of a given gas, an unknown sample of the gas, whether it can be considered as an ideal gas or whether its behavior is approaching an ideal gas or not, can be ascertained by making the gas to undergo Joule-Thomson expansion, right? So that is the relevance of the Joule-Thomson coefficient. Okay, so we can conclude that therefore dt is equal to 0, or t is equal to a constant. That is the conclusion, right? In the next video we will discuss the Joule-Thomson coefficient for real gases, or what you better call as, real gases can be explained by using the van der Waals equation. That is one of the equation for real gases. There are several other equations which has been discussed by many other people, but van der Waals equation is the most common or most nearly successful equation. So we will discuss the Joule-Thomson coefficient for real gases or van der Waals gases in the next session. Okay.